Imagine you're floating in space, staring at one of the most terrifying objects in the universe, a black hole. It looks like a perfect void, an abyss where light itself vanishes. You drift closer, feeling an invisible force pulling you in. At first it's subtle, but suddenly the pull intensifies. Your body stretches, time slows down, and before you realize it, you've crossed the event horizon. There's no going back now. What lies ahead? Will you be crushed into an infinitely small point? Will you enter another universe? Or is there something else, something even stranger, waiting at the center of a black hole? For decades, scientists believed that singularities, infinitely dense points where the laws of physics break down, exist at the heart of every black hole. According to Einstein's general theory of relativity, a black hole's core should be a place where space and time curve to an extreme degree, collapsing everything into a single, infinitely small and dense point. But here's the problem. Infinities don't actually exist in nature. Whenever physics predicts an infinity, it usually means we're missing a deeper truth. Now, for the first time, scientists may be on the verge of answering one of the most mind-bending questions in astrophysics. What's really at the center of a black hole? And the answer could change our entire understanding of the universe. The event horizon, the doorway to the unknown. To understand what lies at the center of a black hole, we first need to understand how these cosmic monsters form. Black holes don't just appear out of nowhere. They are born from the death of massive stars. When a massive star, one at least 20 to 30 times the mass of our Sun, runs out of fuel, it can no longer generate enough outward pressure to counteract its own gravity. This balance is what keeps stars stable throughout their lives, but when the fuel is gone, gravity takes over completely. The star collapses in on itself, creating a region so dense that not even light can escape. This forms the event horizon, the boundary of the black hole. Anything that crosses this point is lost forever. But what happens inside the event horizon? General relativity tells us that all matter falling in gets crushed toward the center, where it disappears into the singularity. This is where things stop making sense, because according to quantum mechanics, infinities cannot exist in the real universe. This paradox has puzzled physicists for decades. If singularities don't exist, then what does? General relativity versus quantum mechanics, the clash of two giants. The real mystery of black holes comes down to a fundamental conflict between the two most powerful theories in physics. Einstein's general theory of relativity explains how gravity works on large scales, shaping galaxies, bending light, and even warping time. Quantum mechanics governs the behavior of the tiniest particles, like electrons and quarks, revealing the strange, probabilistic nature of reality. Each of these theories is incredibly successful in its own domain. General relativity has been tested with incredible precision, from GPS satellites to gravitational waves. Quantum mechanics has led to everything from computers to lasers to the discovery of antimatter. But here's the problem. At the center of a black hole, these two theories completely break down. According to general relativity, all matter is crushed into an infinitely dense singularity. But according to quantum mechanics, a particle can never be confined to a single infinitely small point. Something is missing, a deeper theory that unites both ideas. And scientists think they may finally be closing in on the answer. The missing piece of the puzzle. The conflict between general relativity and quantum mechanics isn't just a minor issue. It's one of the greatest unsolved mysteries in physics. We know that singularities should not exist in reality, but without a complete theory that merges gravity and quantum mechanics, we've been unable to determine what actually lies at the center of a black hole. Physicists believe the answer lies in a long-sought theory called quantum gravity, a framework that would describe gravity in the same way quantum mechanics describes particles. Several groundbreaking ideas have emerged that could replace the singularity with something more physically meaningful. These ideas include Planck stars, gravastars, fuzzballs, and the possibility of a black hole core being a portal to another universe. Let's break them down one by one. Planck stars, a black hole's rebound. One of the most exciting alternatives to singularities is the concept of a Planck star, proposed by physicists Carlo Rovelli and Francesca Vidotto. According to this idea, the immense compression inside a black hole doesn't continue indefinitely. Instead, at an unimaginably small scale, the Planck length about 1.6 to 35 meters, far smaller than an atom's nucleus, quantum effects become dominant and prevent complete collapse. Think of it like a trampoline. If you throw a heavy object onto it, the fabric stretches, but eventually the tension pushes back, causing the object to bounce. The idea behind Planck stars is similar. When a collapsing star reaches the Planck scale, quantum gravity causes an internal rebound. But since time slows down dramatically near the event horizon, from an outside observer's perspective, this process takes billions or even trillions of years. In other words, what we see as a black hole could actually be a star in slow-motion collapse, waiting to explode back outward in the distant future. If this theory is true, it means black holes aren't eternal. They eventually release everything they swallowed. Gravastars, the ultimate cosmic illusion. Another hypothesis suggests that black holes don't have a singularity at all, but instead contain something called a gravitational vacuum star, or gravastar. In this theory, a black hole isn't truly hollow inside. Instead, there's a region of exotic matter that resists collapse. Exotic matter is a type of material predicted by certain quantum field theories. It has negative pressure and can counteract gravity's pull. A gravastar would appear almost identical to a black hole from the outside, with an event horizon and strong gravitational effects. But inside, instead of a singularity, there would be a thin shell of ultra-dense matter surrounding a vacuum-like core. Essentially, this means black holes could just be ultra-compressed bubbles of space-time. If true, this would completely change our understanding of black holes. Instead of being cosmic traps that destroy everything, they could be more like strange, hollow spheres that store energy in unknown ways. Fuzzballs, string theory's answer to black holes. Another intriguing alternative comes from string theory, a theoretical framework that suggests all particles are made of tiny, vibrating strings. According to string theory, black holes don't have a singularity at all. Instead, their interiors are filled with an incredibly dense tangle of fundamental strings, forming something called a fuzzball. Unlike the traditional black hole model, where space-time is smooth until reaching the singularity, the fuzzball concept suggests that the entire interior is a quantum object, a mess of vibrating energy at the smallest scales. This idea solves a major problem known as the information paradox. According to classical physics, anything that falls into a black hole is lost forever. But quantum mechanics tells us that information can't be destroyed. If black holes are fuzzballs, then all the information they consume remains encoded in their stringy structure. This means that instead of an infinitely small singularity, the center of a black hole could be a seething mass of quantum strings, vibrating in ways we still don't fully understand. Wormholes. Could black holes be gateways to other universes? Some physicists propose an even more radical idea. What if black holes aren't just destructive objects but gateways to another universe? This idea isn't new. Theoretical physicist Albert Einstein and his colleague Nathan Rosen first proposed the idea of wormholes, bridges connecting different points in space-time, back in 1935. These Einstein-Rosen bridges are often depicted in science fiction as tunnels through which spacecraft could travel vast cosmic distances instantly. But what if black holes are wormholes? Some researchers suggest that instead of a singularity at the center of a black hole, there could be a hidden passage leading to another part of our universe, or even to a completely different parallel universe. According to this theory, anything that falls into a black hole doesn't actually get destroyed, it just gets transported elsewhere. This is a highly speculative idea, but it raises an incredible possibility. Could black holes be portals to other realities? If so, what happens to the matter that enters them? Does it emerge somewhere else as a new white hole, spewing energy outward? While there's no direct evidence yet, some physicists argue that wormholes could explain certain cosmic phenomena that we don't yet understand, like the rapid expansion of the early universe. Which theory is correct? How will we ever know? Right now, we don't have a definitive answer. Black holes remain one of the biggest mysteries in astrophysics, and testing these theories is incredibly difficult. After all, we can't directly see inside a black hole. We can only observe how it affects its surroundings. But recent breakthroughs in gravitational wave astronomy and the Event Horizon Telescope, which captured the first-ever image of a black hole in 2019, are giving us new tools to study black holes in ways we never could before. Future space missions and advanced telescopes may one day allow us to test these competing ideas and finally uncover what truly lies at the heart of a black hole. So, what do you think? Could black holes really contain bouncing Planck stars? Could they be hollow gravastars? Are they fuzzballs of vibrating energy? Or could they be cosmic tunnels to another universe? One thing's for sure: the answer will change our understanding of the universe forever. The future of black hole research. What's next? While our current theories offer intriguing possibilities, the truth about what lies at the center of a black hole remains elusive. But that might not be the case forever. Scientists are actively working on groundbreaking projects that could provide answers in the near future. One of the most promising developments is the next generation of space-based gravitational wave detectors, such as the Laser Interferometer. Space Antenna, LISA. Unlike ground-based detectors, which are limited by Earth's interference, LISA will operate in space, allowing it to detect even weaker gravitational waves, possibly those emitted during the formation of black holes or even from their mysterious interiors. If black holes do have Planck stars, fuzzballs, or some other exotic structure, LISA might be able to detect subtle deviations in gravitational wave signals, revealing their true nature. Additionally, the next phase of the Event Horizon Telescope, EHT, aims to capture even clearer images of black hole event horizons. If there's anything unusual happening just outside the event horizon, such as energy leakage from a hidden Planck star or signals from an exotic interior, it might be visible in upcoming images. Even more exciting is the possibility that quantum experiments in laboratories could provide indirect evidence of what's inside black holes. Some physicists are exploring ways to simulate black hole conditions using quantum computers or ultra-cold atomic gases that behave similarly to curved space-time. If these experiments reveal behaviors matching certain black hole theories, they could provide strong support for one model over another. A universe full of mysteries, the impact of discovery. If scientists do uncover the true nature of black holes, the consequences will be profound. If Planck stars exist, it would mean that quantum gravity is real, bringing us closer to uniting general relativity and quantum mechanics. If fuzzballs turn out to be correct, it would confirm string theory as the fundamental framework of reality. And if black holes are actually wormholes, it could open the door to the possibility of interstellar travel, or even multiverse connections. These aren't just abstract ideas. They could reshape our understanding of the birth of the universe, the nature of space and time, and even the ultimate fate of everything. Black holes, once thought of as cosmic destroyers, might actually be the key to understanding the deepest secrets of existence. Imagine a future where we could peer inside black hole and see what lies beyond. Would we witness the remnants of a collapsed star still rebounding after billions of years? Would we find a dense, quantum foam-like fuzzball? Or would we see a swirling tunnel leading to an entirely different reality? For now, black holes remain one of the greatest cosmic enigmas, but with every new discovery we're getting closer to unraveling their secrets. And when we finally do, it might just change everything we thought we knew about the universe. So, what do you think? Could black holes be more than just voids of destruction? Are they time machines, cosmic recycling centers, or portals to the unknown? Let us know your thoughts in the comments below. And if you enjoyed this journey into the heart of a black hole, don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of the cosmos. Until next time, keep looking up, because the universe is full of surprises.